Alright, so I thought we'd apply what we already know. What are the three methods for solving systems, guys, from this class at least? Graphing, substitution, elimination. That's what we got. So we can do any of those three. Let's try to stick with substitution or elimination to start out with, and then we'll think about graphing on a couple more, and that'll be all we cover today. So, systems of equations. What do you guys think for that first problem? What might be the better way to go? You think substitution, Mr. Camper? Why?
Because y equals x minus 4, and you could just plug it into the equation.
Where's he looking? Right there, and he's like, that's already substitutable. It says y is this stuff, so take it and stick it in for the other y. So all you've got then is negative x plus that version of y. I don't think I need to distribute, so I don't really need parentheses even. Equals 3. What's the next step now? We combine the x's, so you get like, there's no x, right? Those just go away. So you get negative 4 equals, negative 4 equals 3.
That's not right.
It's not true, is it? It's totally false. So it's not that that is not a solution, it's that no matter what x you put in here, there will not be a solution. This means that's false for all x, because there's no x in there, so x is irrelevant now. So this is no solution. And let's say no solution to what? What were we trying to do? We were trying to find a spot where these two lines crossed, right? There's no solution to the system. There's no spot that these two lines cross. That must mean something special about the graphs.
They're parallel.
They are parallel. We'll come back and look at a couple more problems in a second in terms of their graphs, okay? So let's just leave that. Just in terms of the algebra, we discovered that there's no solution to this system. Okay, how about this one? What do you guys want to do with it?
You could do substitution.
Substitution, elimination.
You could do substitution just
You
now.
can do elimination.
I think this is a judgment call. This is whatever method you prefer. It doesn't really matter. They're both pretty convenient here because you could solve for x really nicely by saying x is 3 plus y. If you add the y to the other side, you could take that and stick it in for x. That'd be a good way to go. I heard more people say elimination. Why is it nice to do elimination? So what do you guys want to target, the x or the y?
It'd be targeting both.
Okay, this is interesting. So we're targeting both, but make a decision. Let's just say x. We could make x go away if this was negative 5x. So if that's negative 5x, we got to multiply this by
Negative 5 to get positive.
by negative 5, so that would be positive 5y. So this is the cheater way, dangerous. You guys see what I'm doing? I'm writing this in there, dangerous. You should probably write your problem down again. This is dangerous. So then this would become
Negative 13, everything.
negative 15, right? Times negative 5,
Zero
right?
equals zero.
So now if we add these together, what's going to happen?
You're gonna have nothing.
Gone. Gone. Oh, gone. So this really says 0 equals 0. Well, is that true or not?
Yes.
Is that all solution?
That is all
The
solution.
word all, oh man, make me cringe, Logan. You're right though. No matter what you plug in for x and y, they're the same line. Let's go back to the original problem and look. So the way you'd write this is there are infinite solutions. That does not mean that everything is a solution, because as you'll see when we graph this in a sec, everything is not a solution. There are infinite solutions where, Miss Newitt?
Where it equals zero.
On the same line. That's a good way to say this. On the same line. Anything that's off that line is not an answer to this problem. Does that make sense? That's why I'm saying all is my nemesis. Okay? So a couple people, Miss Newitt identified that these were the same line a second ago. Let's go back and take out our blue modification. What was the original problem again? Wasn't it,
X plus y.
it was x minus y
So equals 3.
equals 3, like that, right? That's nice. Minus e. Can you look at that, guys, and tell me that that is the same line like she said?
Yeah.
I think she was thinking abstractly, but
Yeah,
looking
it's
at
just
that,
different points
that's
on it.
the same thing, isn't it? This one is that one scaled by 5. It's the same thing, so of course it has an infinite number of solutions to the same thing being itself. So there you go, we'll graph it in a second. Let's do that one more time before we think about graphing these though. So this is very key the way you write this out right here, okay? Matters a lot. So, what do you guys think for this one? Substitution or elimination?
I'm confused on this one.
Well, can you eliminate something right away? Do the y's go away?
Yeah.
Wait, no.
You'd have to scale it, right? This one, just like you said on the first one though,
Yeah, you just-
doesn't it say y is the stuff?
yeah.
So you can just put the stuff in for the y. I think substitution is probably the way to go. If you're confused by this parentheses, distribute it and rearrange it before you decide. I don't think I need to, because it says y is this stuff. I don't care what that stuff is. It could be a parabola, an exponential function, something weirder. Whatever it is, you can put it in there if you want. Because that's what it is. That's why. So now I have the stuff. Minus 3 is x. That'd be one way to do this problem. There's a whole bunch of them. So now we can distribute 4x plus 4. Let's see, that says 4x, 4 minus 3 is 1. Right?
Yeah, you minus 4x.
Minus. So you get 1 equals
Negative 3x.
negative 3x. Divide. And you get negative 1/3 for x. We have negative 1/3 for x. I think I can put it in either one. This one looks good. So I'm going to go y minus 3 equals our x. Solve for y. It's going to add your 3. So you get y is 3 minus 1/3. I think that's one that you can do with common sense. 3 minus 1/3 is 2 2/3. If you really want to make it look nice and be more functional in algebra 2, I think you'd want to make a common denominator. So the common denominator is thirds. So you could say over here that y is 3 minus 1/3 and make a common denominator out of that 3. So divide it by 3 and multiply by 3. So you get 9 minus 1 of those thirds, which means 8/3. Now 8/3 and 2 2/3 are both answers. I think 8/3 you'll find is more useful in future classes. So these lines in fact cross at negative 1/3, 8/3. I don't think you'd ever get that from graphing them. So now that we know how to solve systems, it's important to be able to classify them. What does the word classify mean?
Telling where something belongs.
Yeah, where something belongs. That's very nice. Like in taxonomy and biology. Yeah. So I think it's also just like naming. A not as sophisticated way of saying it is it's a naming system. I like yours too, though. Okay. So let's think about 2 lines. So we're just going to be classifying. I should have said classifying linear systems. So if you're classifying linear systems, there's 3 possibilities. You guys have been talking about these 3 possibilities. Let's draw what each one looks like. What are the 3 possible things 2 lines could do interacting with one another?
Cross each other.
They could cross each other, so I'm going to draw random 2 lines. They could do something like that. They could cross each other in any orientation, even if they're perpendicular, they're still crossing each other. What else could they do?
They could be parallel.
They could be parallel, so it could be lines like this. If they have exactly the same slope. So that's how we're going to decide these things now, okay? And the other possibility, which we saw a second ago, highlighted a bunch, was that there could be one line, I don't know, something like this. And then the other line could do exactly the same thing. That sounds like the least common possibility, doesn't it? If you think about two lines, like this is extremely rare. Which one of these do you think is the most common possibility if you have lines in the wild? The ones that cross, right? Like that's going to happen most of the time. The only way this happens is if they're exactly the same. The only way this happens is if part of it's exactly the same, the slope part, right? Over here is all other possibilities. One of these three things has to happen. So we have special names for these, so you need to be able to know those names. This guy, the slopes are completely not dependent on one another, so we call these independent lines. That's how I remember it. When I was in high school, it's not like they gave you a reason, you just remembered it. This makes sense, I think, because the lines are different. They're independent, they don't affect each other. Does that make sense? And you get an answer, so it's logically consistent to try to solve this problem. So it's called consistent. That's the reason I think of consistent as the answer. Okay? This problem, you don't get an answer, so it doesn't really make sense to try to solve it in the first place. You might try because you didn't recognize that. Like we're going to probably not recognize it on one of these. So this is called inconsistent. Very nice. And these two lines could be any parallel combination, so technically that's independent, but since it doesn't even make sense to solve it, I think that's enough for a name. You know what I mean? So what do you guys think about this one, based on the names we already have? Is it consistent or inconsistent?
Consistent.
It's consistent. Why, Richard?
Because it's infinite solutions.
Because you get an answer.
Yeah.
So it made sense to pursue one in the first place. And what do you guys think? Dependent, independent? This is dependent. These lines very much depend on one another because they have to. If they're exactly the same, they very much are dependent on one another. Does that make sense? So how many solutions? That's the easy part. You guys already kind of knew it. When we get one solution, like you did on your little exit slip or quiz, it's going to be this.
Are
Go
the
ahead.
parallel lines, are they dependent too?
What do you guys think? Dependent or independent on this?
They're kind of both, because one of them has to be the same, but if the other
The
one...
slopes have to be the same. So yeah, that's why we don't even really go there on that one. It's not really an appropriate name tag dichotomy is what you'd call that. Okay, so how many solutions here though? You guys knew it? None. Let's just say no solution. And how many over here? We said infinite solutions. Where?
This is on the line.
On the line. Because this isn't an answer, this isn't an answer, that's it. Okay? So, how do you decide on some system examples like the three I have here, which one of these three it falls into? So these problems don't say solve the system. Be careful about the directions on their assignment this time. Most of them don't. Some of them say solve the system, some of them don't. If they say classify, they're just interested in the names. If they're interested in the names, the best way to do it is graphically. Think about the picture. So if I want to think about the picture on this guy, what do I have to do first? Slope-intercept form. So I need to solve for y on both. This bottom equation, what do I have to do to get y by itself? I need to add, so I'll show a little work here. So I'll get what? Y equals 1 plus 1/3 x. All right, I can think about that. And on this one, what I need to do to get y by itself?
You got it.
Divide by 5 on both sides. So you get y is 1/5 x right there, minus 2/5. Now just looking at that, we could of course draw these lines, you know, and get a real nice drawing, but you shouldn't have to. That right there should tell you which case you fall into. Which one of the three cases is this one? Are they cross, are they parallel, or are they identical? They're clearly not identical, right? Are their slopes the same? No, so how many solutions are we going to get if we try to solve it? One. So we'd call this guy consistent, independent, we'd get one answer. right? That's all you got to do on those problems. It's all about thinking about what the graphs would look like. Okay, this is getting a little bit messy. Let me get this one out of the way. So the second one, what do we have to do to get y by itself here?
U minus the x.
Rewrite it. So this is equal to y equals 13 minus x. And here, with the 4. So you get y equals negative x minus 4. So now look at that carefully. Think about what the graphs would do. Is it going to be parallel lines, the same line, or are they going to cross somewhere?
They're gonna cross. Oh, they're parallel.
Slope here says down 1 over 1. Slope here says down 1 over 1.
Oh, so they're gonna be
Same slope.
inconsistent.
Same intercepts?
Yeah, it's inconsistent.
No.
So it's gonna be
These lines would be like this.
Yeah.
One starts up at 13 and goes down. One starts at way down at negative 4. They're more like this, yeah? But they're parallel. So I could draw them, but all they asked me was to classify. This has no solution. If you tried to do it like we did at the beginning of the lesson, you'd see something would happen like 2 equals 3. You know? You get something like 2 equals 3. It's not true. All right, let's try it with one more. Looking at this guy, when I start looking at it, I really don't know. I don't know which case this is going to fall into. I've got to solve for y before I know that. Or, I mean, you could, of course, think about these without solving for y, but that's an alternative. So let's just stick with our strategy. So on the top one, I think I'm going to subtract x first. So I'll get this. If I subtract x over to the other side, I'm going to distribute here first. And then I'm going to add the 4. Okay? And then on both those I need to get rid of the 2's by dividing. So I'll go ahead and divide. Here I'll divide by negative 2. And we'll see what happens. This is equal to, let's see, y equals 4 over 2 is 2. That's minus a half x. That's minus a half x. 4 over 2 is 2, and that's a negative. So what do you guys think?
Inconsistent.
Looks inconsistent, right? Same slope, different intercepts. Let's make sure I didn't make a mistake. There were lots of negatives. There's a place where I'd probably check my work. So let's see. I distributed here. Minus became, plus became minus. That looks good. Added my 4, that looks good. Divided by negative 2, that's negative, good. Yeah, this one's inconsistent. How can I change this problem to get something that is infinitely many solutions? Can you guys help me? Change something in the original problem in the black so that you'd make this be infinite solutions. It's so close. Negative 4? So Richard's saying if you just made that negative 4, then you'd have negative 4 right here. Negative over positive is negative 2. Now these are identical. So this would be consistent, dependent, or infinite number of solutions. Okay? So it's all about naming when you see that word classify, and you should be trying to use mx plus b to help you out. All right.